Okay, let's dive in. So finding new medicines, it's this massive challenge, right? You've got these huge virtual libraries, millions, sometimes billions
Yeah,
of potential drug molecules.
absolutely billions. It's staggering.
And a key step, maybe the key step early on, is molecular docking.
Mm-hmm. That's basically figuring out if a potential drug, the ligand, can physically fit and bind to a target protein, like a key in a lock.
The very, very complex lock.
Exactly. And you need to know if the key fits. But the traditional ways of checking, well, they can be effective, sure, but often painfully slow.
Especially with these enormous libraries we're talking about now.
Right. So researchers often have to make this trade-off. Do you want speed to screen millions quickly, or do you want accuracy to be sure you found something good? It's tough.
Yeah, this sounds like a real bottleneck.
Yeah.
So you've shared some sources on a newer approach, something using deep learning called KarmaDock. What's the idea there?
Well, KarmaDock is pitched as a deep learning tool specifically for pocket-guided docking.
Pocket.
Yeah, meaning it really focuses on that specific binding site, the pocket, on the protein where the drug needs to fit. And the goal is kind of ambitious.
Yeah.
Integrate high speed, accurately predicting how the molecule binds the pose, and even correcting it and estimating how strongly it binds, all in one package.
Okay, speed, pose, and strength. And it uses a three-stage model. How does that work, roughly?
Yeah, 3 stages. First, you've got encoders. They basically take the protein and ligand structures and translate them into data the AI can understand, sort of like prepping the ingredients.
So that's stage one, prep.
Stage 2 uses something called equivariant graph neural networks, EGNNs. These are particularly good with 3D structures and how they relate spatially.
So that's for figuring out the actual fit, the 3D puzzle part.
Exactly. Generating and then refining the potential binding poses. How does this molecule actually sit in that pocket?
Okay, and stage 3.
Stage 3 uses a mixture density network, an MDN. It's a type of probabilistic model, and its job is to score the poses, basically, estimate how likely and how strong that predicted binding interaction is.
So prep the molecules, figure out how they fit together in 3D, and then score how good that fit is. Makes sense.
That's the gist of it, yeah.
And the sources mentioned some, well, pretty impressive results. What's the headline?
I think the thing that really jumps out is the speed. It's just, wow. The paper mentions KarmaDock screened 1.77 million compounds in 8.4 hours on one single GPU.
8 hours, okay. How does that compare?
Well, compare that to a standard tool, Autodock GPU. They estimate the same job would take over 57 days.
Whoa, wait, days? 57 days versus 8 hours?
Yeah. It's a massive difference.
That's potentially transformative. For you listening, just think about scaling that up. Screening hundreds of millions, billions of compounds. That kind of speed changes the game entirely.
It really could accelerate that initial phase of discovery.
But like you said before, speed isn't the only thing. Is it accurate? You don't want to be fast and wrong.
Absolutely crucial point, and the data suggests it holds up well there too. The sources show it performing really well on standard benchmarks, things like CASF 2016, Decoys 2.0. It has higher enrichment factors.
Enrichment factors, meaning it's better at finding the needles in the haystack, the actual good drug candidates among all the duds.
Exactly. Much better, apparently, than traditional methods and even some other deep learning approaches. And they also tested it in a real-world scenario, screening for an inhibitor for a protein called LTK, and it successfully identified one that was later validated experimentally.
Okay, so it's finding real hits, not just doing well on tests. That's good. And the sources also mentioned something about flexibility, that it handles flexible molecules well. I know that can trip up older methods.
Precisely. Molecules aren't always rigid blocks. They can wiggle and bend. KarmaDock's ability to manage that ligand flexibility seems to contribute to its better performance in docking and screening.
That makes sense. Things aren't usually perfectly rigid in biology.
Not at all. Now, it's not perfect, of course. Like any new tech, there are still things they're working on. They mention needing to ensure the predicted poses are always, chemically sensible after some refinement steps. And also incorporating protein flexibility more fully. Right now, it's more focused on the ligand's flexibility.
So semi-flexible, focusing on the drug molecule moving around.
Got it.
Okay, so summing up, incredibly fast, seems highly accurate on tests, and in practice, handles wiggly molecules well, but still some technical refinement happening.
That's a good summary. The potential seems huge.
So, thinking about the bigger picture here, what does this mean for you, the listener? What's the takeaway?
Well, it really brings up a fascinating question, doesn't it? If you can suddenly screen these vast chemical libraries, potentially hundreds, even thousands of times faster and maybe more accurately, how fundamentally might that change the pace of drug discovery? Could we see completely new therapies identified and developed much, much faster than we ever thought possible?